Institute of Aeronautical Engineering, Tech Talk, AAT-1, name N. Venkat Sai, roll number 23951802226, branch Electrical and Electronics Engineering, subject Power Electronics, topic Voltage control of AC loads with R and RL characteristics. Voltage control of AC loads. This presentation explores the critical role of AC voltage control for both resistive and inductive loads. We will focus on thyristor based single phase AC voltage controllers essential for applications in motor control, heating and lighting. Understanding AC loads, resistive versus inductive. Resistive load. Current and voltage are in the perfect phase synchronization. Example include electrical heater and incandescent light bulbs where energy is primarily dissipated as heat. Inductive loads. Current lags behind voltage due to the presence of inductive reactance. Common example are electric motors and transformers which store energy in magnetic fields. RL loads combine resistance and inductance, leading to phase shift and waveform distortions. Single phase AC voltage controllers. How they work. AC voltage controllers utilize thyristors to precisely regulate the conduction angles, also known as phase angle control. By connecting single phase regulations in parallel, they enable current flow during both positive and negative half cycles of the AC waveforms. The output voltage is finally adjusted by altering the firing angle, which dictates when the SCR begins conduction. Voltage control with resistive loads. Voltage waveforms. The output voltage closely mirror the source voltage, initiating conductions only after the SCR's firing angle is reached. Current behavior. The current waveforms remains perfectly in phase with the voltage waveforms, reflecting the resistive nature of the load. Output control. The output voltage is smoothly regulated by adjusting the firing angle across its full range 0 degrees to 180 degrees, similar to a lighter dimmer circuit. Voltage control with inductive loads. Current lag. In inductive loads, the current waveforms consistently lags behind the voltage due to the inherent inductive reactance of the circuit. Conduction continuity. Unlike resistive loads, the current does not absolutely stop. Thyristor conduction may continue even after the voltage crosses zero due to energy stored in the inductance. Complex waveforms. The phase shift and extended conduction create disrupted waveforms, making control and analysis more intricate compared to resistive loads. One more. Explain. Voltage control with inductive loads. Current lag. In inductive loads, the current waveforms consequently lags behind the voltage due to the inherent inductive reactance of the circuit. Conduction continuity. Unlike resistive loads, the current does not abruptly stop. Thyristor conduction may continue even after the voltage crosses zero due to energy stored in the inductance. Complex waveforms. The phase shift and extended conductions create distorted waveforms, making control and analysis more intricate compared to resistive loads. Waveforms and conduction angle analysis. The conduction angle is crucial, defining the period during which is the thyristor conducts. For purely resistive loads, conduction naturally ends when the voltage crosses zero. However, with inductive loads, energy storage causes conduction to extend beyond this point. This fundamental difference leads to significantly distinct voltage and current waveforms between R and RL loads, requiring carefully consideration in design. Second, waveforms and conduction angle analysis. The conduction angle is crucial, defining the period during which the thyristor conducts. For purely resistive loads, conduction naturally ends when the voltage crosses zero. However, with inductive loads, energy storage causes conduction to extend beyond this point. This fundamental difference leads to significantly distinct voltage and current waveforms between R and RL loads, requiring carefully consideration in design. RMS voltage and power calculations. RL load complexity. Calculations for RL load are more involved, factoring in phase shifts and continuous current flow. Resistive load formula. For resistive loads, RMS voltage is derived from the integral of the sinusoidal waveforms of the from the firing angle. RMS load voltage. The effective load voltage is directly dependent on the firing angle and the specified type of load conducted. For instance, with a 100 volts peak voltage and a 60 degrees of firing angle on the resistive load, the RMS voltage is approximately 35.4 volt. Once again, I will repeat RMS voltage and power calculations. RL load complexity. Calculation for RL loads are more involved, factoring in phase shift and continuous current flow. Resistive load formula. For resistive load, RMS voltage is derived from the integral of the sinusoidal waveform from the firing angle. RMS load voltage. The effective load voltage is directly dependent on the firing angle and the specified type of load connected. For instance, with a 100 volts peak voltage and the 60 degrees firing angle on a resistive load, the RMS voltage is approximately 35.4 volts. Practical applications and considerations. AC voltage controllers are vital in single phase half wave and full wave controlled rectifier circuits. They enable precise control of average load voltage and current by adjusting the firing angle and considering load parameters. Common applications include variable speed control for motors, precious regulations of heating elements, and sophisticated lighting dimming system. The accuracy of triggering circuits and precise timings are paramount for effective control in the system. Protection and practical considerations. Overvoltage protections. Critical for inductive loads to prevent damaging voltage spikes during switching. Commutation methods. AC circuit typically relay and naturally commutations, but forced commutation may be necessary in specific scenarios. Stunber circuits used to protect thyristors from transient voltages and current surges, ensuring device longevity. Efficiency factor load characteristics significantly influence the overall design and operational efficiency of the controller. Summary and key takeaways. Vers- Versatile control. Thermistor based voltage control is highly effective for both resistive and inductive AC loads. Simplicity and resistive loads. Control is straightforward due to the in-phase of voltage and current, making them simpler to manage. Complexity of inductive loads require precious timing and design due to the current lag and continuously beyond zero crossings. Robust design. Proper controller design, including protection circuits, is essential for safe and efficient AC voltage regulation in diverse systems. Thank you.